All right, let's go through some of these multiple choice questions together here. All right, so for number one, it says for this density curve, aka this uniform density curve, what must the value of x be right here? So we know it goes from 0 to something, but we don't quite know what it should go to. Now, the vertical axis, this represents our probability of x, of the values that are down here. So I guess I shouldn't say x per se, but the probabilities in general. All right. So what must always be true about any density curve, regardless if it's a uniform or a normal or whatever case it may be, is that it must have an area equal to 1 or 100%. And so we're going to treat that as a rectangle, and we know the area's got to be 1 or 100%. The base has a length of x, right? To get from 0 to x, that would be a length of x, and the height is 2/5. So what times 2/5 is going to give me 1? Well, we could multiply both sides by the reciprocal of 2/5, which is 5/2. That'll knock out the 2/5. And 1 times 5/2 is 5/2, which has a value of 2.5. So when x is 2.5, then this is an actual legitimate density curve with area of 1. All right, number two. For this density curve, what percentage of the observations lies between 0.5 and 1.2? All right, so let's see. Half of 2.5 is going to be 1.25. So we'll just say that this is just less than half. We'll call this the 1.2. And then 0.5, it really doesn't matter kind of where exactly you put it to the left of there. So we'll say it's right there. So we want to know what percent of observations lie between 0.5 and this 1.2. So we just have a smaller rectangle to work with. So we're still going to use base times height. And so the base is the difference between 0.5 and 1.2, which would be 0.7. And the height is still the 2/5, which if you want, you could convert to a decimal. And 2/5 is the same as 0.4. So 0.7 times 0.4 is going to give us 0.28, which is 28%. All right, number three. If Bryce's standardized score on a recent test was 1.1, then what percentile is he in, assuming the original test scores came from an approximately normal distribution? Oh, right. So we know we're dealing with an approximately normal distribution, but we don't know the mean or the standard deviation, so we might be dealing with a standard normal distribution. So in the middle, the mean is going to be 0, standard deviation is worth 1, and we were told that his standardized score is 1.1, and the standardized score is a z-score. So this actually does work perfectly for this standard normal distribution because these values down here are z-scores. So that means Bryce's score is 1.1 standard deviations above the mean because it's positive, not negative. So let's just say here's Bryce. Here's his z-score of 1.1. And if I want to know what percentile he's in, I got to remember what the definition of a percentile was. It was the percent of values that fall below. So we need to figure out all of these values that fall below Bryce's 1.1 z-score. Now, looking at this graph, and as long as I've made it fairly realistic, I can already tell, from the mean down is 50%, so I know my answer is going to have to be bigger than 50%. So just logically speaking there, I know the answer can't be A, B, or C because all of those are smaller than 50%. So now, even if I don't know how to do this problem, at least I've narrowed it down to a 50-50 guess. Is it 84% or 86%? Now, since we were told that this is an approximately normal distribution, now if we want to find that area, we can use the normal CDF command. And so our lower bound is negative infinity because this is our furthest left shaded region. Our upper bound is going to be Bryce's 1.1. The mean is going to be the 0 for the standard normal. and the standard deviation is the 1 for the standard normal. And so now, if I plug all that into my calculator, I should come up with the answer of 86.43% or 0.8643. So Bryce is in, I guess I should state, as the 86.43rd percentile. All right, number 4, Dr. Doofus, terrible mathematician. He incorrectly calculated test scores by shorting everyone 10 points. How dare he? Statistics for the incorrect test scores are Q1 at 44%, median at 64%, Q3 at 75%. What will the corrected median and IQR be? So first we need to discuss what really needs to happen mathematically here. If Dr. Doofus shorted everyone 10 points, what is he going to need to do to make up for that? Well, he's going to have to add the 10 points back in, right? So he needs to add, well, not 10% per se, but 10 points. We'll just do 10 points. He needs to add 10 points back to their original scores, okay? So if all we're doing mathematically is adding, we need to think about what does adding do to, and let's start with the median. What is adding do to a measure of center? And adding is affected by measures, or I should say rather, measures of center are affected by addition. So we would take our old median and we would need to add 10 points back onto it, or 10% in this case. And so the median should, the median should be 74%. So we know it's not A, we know it's not B, we know it's not C, but it's either D or E. We just got to figure out is the IQR 41 or 31. All right. So now, and we can do this one of two ways, and we'll do both, of course, because I want to make sure you guys understand everything here in multiple ways. We could do this as the old IQR. Basically, the wrong, incorrect IQR would really be Q3 minus Q1, and that was 75 minus 44, which is what, 31%. So this was the incorrect IQR. But if we add 10 points, will the adding affect the IQR? Will it affect a measure of spread? And it doesn't. So it should stay 31. And so that means our correct answer is going to be D. Now, I mentioned I'm also going to show you kind of a secondary way of doing this. Even though the adding 10 points did not affect the measure of spread, the 10 points does affect other positional values, like Q1 and Q3. So really, the correct Q1 really should be 54%. And the corrected Q3 really should be 85%. And so if we still subtract 85 and 54%, we're still going to end up with 31%. Okay, so there's two ways. You could either adjust the Q1 and Q3 and still realize it's the same IQR as it was before, or calculate the old IQR and go, well, it's going to be the same one because adding doesn't affect measures of spread. Number 5, using the ogive to the right, or really below to the right, related to test scores, determine the approximate value of the IQR. So again, IQR, Q3 minus Q1, we need to find two values here, the third and first quartiles. Now, the third quartile, aka the 75th percentile, and Q1 is the 25th percentile. The vertical axis here is going to represent our percentiles. You might also see it represented as the cumulative relative frequency. All right, but these are essentially either going to be written as percents, or maybe they're written as decimals from 0.0 up to 1.0. So the 75th percentile, we would need to go to 75% on our percentiles, and why didn't that show up in color? Oh, I bet it's behind. It's behind. Okay, I'm going to have to legit try to draw this as horizontal as I can here. So going horizontally across to the ogive, we're going to see where it hits the graph, and then let's drop as best as we can vertically down. So we can see there's where the third quartile should be, at a score of, we're going to have to estimate, like 82, 83. And then the 25th percentile will come down here. We'll try to go across horizontally as best as we can. Looks like it's hitting about that point right there, and drop straight down, and that looks like a much closer 75. So if I subtract those away, then I get an approximated IQR of, what's that, about 7%. And so what's the closest answer? 8%. Number 6, the time it takes for students to complete a standardized exam is approximately normal. So this is a good thing to know. Let's make some either highlighting or underlining. We know we're dealing with an approximately normal distribution with a mean of 70, so mean goes in the middle, and standard deviation 10 minutes. So I could easily go, 1, 2, 3 standard deviations above, add 10, add 10, add 10, go 3 standard deviations below, subtract 10, subtract 10, subtract 10. So 60, 50, 40. So there's a good model of what we're dealing with. So this says, using the 68, 95, 99, 7 rule, the empirical rule, what percentage of students will complete the exam in under 1 hour? Well, we got to do just a small calculation here. So in under an hour is under 60 minutes. Because you got to realize the units of the 70 and the 10 for the mean and the standard deviation are in minutes. So I'm making you do one thing to know that an hour is 60 minutes. Here is 60 minutes. And so we need to figure out what is the area under the curve from 60 all the way down, really to 0, right? We don't stop at 40 because some students could turn it in 30 minutes or 20 minutes or 10 minutes, or maybe they get it and they turn it in a minute later. So they're really far, like down here. So remember, this thing keeps going on and on and on forever. Just the area is not very much down that way. Now, looking at our graph, we can tell that that's easily less than half of the curve, right? Because the mean is exactly half to the left of it and half to the right of it. So I know, just by pure logic alone, the answer can't be over 50%. So I can cross off A there. Now, using the empirical rule, you could use normal CDF on this. But I kind of encourage you just to kind of think about and use the empirical rule. So between one standard deviation, that's 68%. Between 2 standard deviations, that's 95%. And between 3 standard deviations, that was the 99.7%. Now, what I see in this problem is I'm dealing with less than half of the distribution, right? So I'm going to think about that 68, and I want to think about it cutting that 68 in half right at the mean. And so that's telling me that this chunk, 1 standard deviation below, is 34%. But again, how much area is there from the mean all the way down forever and ever and ever and ever? 50%. So I don't want this 34% in that 50%, so what's left over is 16%. Now, if you use normal CDF, you're going to get an answer that's really, really close to 16%. Number 7, Jesse and John are twin brothers who run track but different events. Jesse ran in the 100-meter dash with a time of 10.34 seconds. Assumed times for the 100-meter dash are approximately normal, so we're dealing with a normal distribution, with a mean and a standard deviation of those numbers listed. John ran in the 200-meter dash with a time of 20.52 seconds. Assumed times for the 200-meter dash are approximately normal, with mean of that number and standard deviation that number. Which brother did better and why? And so if you look at the first answer choice, it says John, because if you double Jesse's run time, and if we double Jesse's run time because he ran the 100-meter dash and John ran the 200-meter dash, well, if we double a 100-meter dash time, well, it's like he ran a 200-meter dash, right? So can we really compare a 100-meter dash time, even if it's doubled, to a 200-meter dash time? And any track athlete would know that, you're really just going to flat out sprint on a 100-meter dash. In a 200-meter dash, you're still going to sprint, but you can't sustain that same endurance for twice the distance. Okay? So realistically, that can't be the answer here. But if you look at all the others, they talk about comparing standardized scores, aka z-scores. So what we can do is look at some z-scores. Now, even though these are approximately normal times, you could use normal CDF and see kind of where they're at, like what percentile they're in. But this is specifically asking about standardized scores. So let's calculate some z-scores. So let's get Jesse's z-score. So we'll have x minus mu over sigma. And so Jesse's z-score, so we're going to need Jesse's actual time. Jesse's time was 10.34, so that's the x, minus the mean, and that mean was 10.42, divided by the standard deviation, 0.33. All right, and then we'll do the math here in a second. So let's go jump over. Let me grab a different color. And let's do John's. There we go. John's z-score. But again, same formula, x minus mu over sigma, except John's time was 20.52. 20.52. Now, come on, pen. Stop being crazy. Minus mean, what was the mean? 20.86. Divided by standard deviation, 0.42. So without actually calculating anything, one observation we can make here is that we can see Jesse was faster than the mean, and we can also see that John ran faster than the mean. So here is where you could try to just look at it and go, well, if one brother ran over the mean and one brother ran under the mean, well, then you know clearly who did better, right? Because one was faster on average and the other one was slower on average. But both of these brothers were faster than average. So now we're going to need to grab a calculator and do some calculations here. So let's see, for Jesse, 10.34 minus 10.42, divide that number by 0.33, and I get as a z-score, it's going to be negative because he's under the mean, he's faster than average, negative 0. Really it's 2 4s repeating. And then if I look at John's, 20.52 minus 20.86 divided by standard deviation 0.42, I get negative, again, because I know he's faster than average, 0.81, rounded. So which brother did better? And in this case, is it the higher the z-score, the better? And in terms of track times, no, higher is not better. So we wouldn't say that Jesse did better, because actually he's closer to being average than John was. John is further away from the mean. He is faster. He's almost 1 standard deviation away from the mean. Meanwhile, Jesse's time is hardly even a quarter of a standard deviation below the mean. So I would say John is the winner here because his standardized score is lower than Jesse's standardized score. So I would say the answer to this one is D. And you always got to keep in mind, if of the context of the problem, is bigger always better? And in this case, bigger isn't better because we're talking about race times. All right, number 8. Caffeine content of venti Starbucks coffee drinks is approximately normal. All right, so let's make some notes here. We got an approximately normal distribution. We have a mean, 415. But they didn't tell me standard deviation. Ooh, okay. Well, let's see what else is going on here. A randomly selected venti-sized Starbucks coffee contained 418 milligrams of caffeine, which has a z-score of 0.8. Approximately what percent of all venti-sized Starbucks coffee drinks have caffeine content greater than 408 milligrams? All right, so we know we have an approximately normal distribution with a mean of 415, but we are missing a standard deviation. Now, that second statement there, they said, hey, you know what, we went by Starbucks and we grabbed a venti-sized Starbucks coffee, and that one coffee contained 418 milligrams of caffeine, which gave it a z-score of 0.8. So, hey, they're talking about z-scores. So that's x minus mu over sigma. We know what mu is, the mean, it's 415. And we know what x is because that is the specific number of milligrams in that cup of coffee. Now, again, we don't know the standard deviation, but hey, we do know the z-score. They gave us that. So this is 0.8, which means the only variable of interest left over is the standard deviation. So we get to solve for the standard deviation, and really the quick way of doing that is we can swap the standard deviation for the z-score of 0.8. It can now go down here, and so we'll have 418 minus 415 divided by the z-score of 0.8. So really that's what? 3 divided by 0.8. And so I get a standard deviation calculator. 3 divided by 0.8 is 3.75. Okay, so we know the standard deviation is 3.75. So now, maybe we can actually answer the question that they asked. Approximately what percent of all venti-sized Starbucks coffees have caffeine content greater than 408? So let's let X represent caffeine content. We want all the values, all the coffees that are greater than 408. So really they're asking us to figure out what is the probability or the percent that we would have coffees that are exceeding 408 milligrams. Well, now here's where we can shine with the normal CDF. And so let me just draw a quick curve up here. So we knew the mean was at 415. And we need to find 408 in this normal curve. Okay, so let's go find 408. And really that's going to be somewhere below the mean. You know, how many standard deviations is that below the mean? You could approximate, how many standard deviations that's going to be, about 2-ish maybe. But really you could just know that 408 is going to be to the left of 415. And then we're going to figure out all of this amount that's greater than 408. All right? So we know, just by looking at this picture, the answer is going to be more than 50%. So it's not going to be A. I'm not hitting everything, so it can't be 100%. So I got a pretty good feeling it's either going to be B or C. So lower bound is the 408. Upper bound is like the most jacked up coffee you've ever had on caffeine. So 9999999 or infinity, theoretically. Mean 415. And standard deviation that we had to figure out, except I wrote it in the wrong spot, 3.75. And so now if you type that in your calculator, you should get 0.9690 rounded, which is our answer choice B. So these will be pretty common questions, multiple choice wise, where you're just going to have to do a little bit of kind of background work before you can really answer the final question. All right, number 9, the heights of male adults are approximately normal, with a mean of 1.7 meters and a standard deviation of 0.2 meters. Apparently they are not from the United States, because why are we in meters? In a population of 400 male adults, how many would you expect to have a height between 1.4 and 1.6 meters? So consider, we have an approximately normal distribution. We know the mean is 1.7. And we know the standard deviation is 0.2. So I could go, 0.2, 0.2, 0.2 to the right, 0.2, 0.2, 0.2 to the left, but I don't really need to do that. I want to know the percent, or how many people, right? It didn't ask me what percent of people, how many people in this population of 400 would be between 1.4 and 1.6. Well, I know 1.4 is to the left of 1.7, and 1.6 is going to be to the left of 1.7. So I'm just going to estimate. We'll say, I don't know, here's where 1.6 is, here's where 1.4 is going to be. And I can figure out what percent of values are between 1.4 and 1.6. So I get to use normal CDF. I know the lower bound is going to be starting at 1.4. Upper bound goes up to 1.6 with a mean of 1.7 and a standard deviation of 0.2. And let's see what the calculator tells me. Let's see, what do we say? 1.4 to 1.6, mean 1.7, standard deviation 0.2. And that gives me 0.2417. And initially you might go, oh, look, there's 24. Cool. But I didn't ask for what percent. I asked for how many out of 400. We would expect 24% to be between 1.4 and 1.6. So what is 24% of 400 male adults? Well, that's just about a quarter, right? 25% would be a quarter, and a quarter of 400 would be 100 people. So this is going to be something really, really close to 100. And 24% of 400 is 96. So I would expect around 96 out of these 400 male adults to be between 1.4 and 1.6 meters, which closest gets me to that 97. All right, the final one here. A soft drink machine can be regulated so that it discharges an average of mu ounces per cup. If the ounces of fill are normally distributed, so we know we have a normal distribution, with a standard deviation of 0.4 ounces, what value should mu, the mean, be set at so that 6-ounce cups will only overflow 2% of the time? So we know we're dealing with a normal distribution, but we don't know what the mean is, right? But we want 6-ounce cups to overflow only 2% of the time. So overflowing, we got to think about where this 6-ounce cup would go, and overflowing versus underflowing. Well, overflowing would mean if I had a 6-ounce cup, that 6-ounce cup would go right here, 6 ounces. And so if it overflowed, that would mean that 6-ounce cup was filled with more than 6 ounces. So we're saying that this represents 2%. Okay, so we need to have a mean that has a standard, or have a distribution that has an unknown mean that has a standard deviation of 0.4 ounces, where this only happens 0.02 or 2% of the time. So if you think about, like, I don't know, can we use normal CDF? Let's see, normal CDF, lower bound 6 ounces up to, a jumbo size cup, crazy jumbo size cup, with a mean of, oh shoot, but we don't know what the mean is. But we do know that the standard deviation is 0.4. And what answer would we be looking for to go from 6 up to infinity? We would be looking for 2%. So here's a strategy that you could use on this multiple choice question and any other multiple choice questions. You could take these answer choices and you could start plugging them in one at a time for the mean. And whatever one of these gives you 2% or really, really close to 2%, must be the correct answer. Now, there are some answer choices over here that we can cross off the list. All right? And which ones would those be? Well, looking at this picture, we know the mean has to be smaller than 6 ounces. Because if the mean was 6 ounces, then that would mean that cups would overfill 50% of the time, right? So we know it can't be 6, and it can't be more than 6, because then the means would be over here. That's not right. It needs to be over here. So either the mean is 5.18 or 5.60. So even if you started guessing and checking, at least you would find the correct answer out of one of the first two. But how do you do this without guessing and checking? Good question. If we can't use normal CDF, then that's a really good indicator. We're going to have to use inverse norm. So inverse norm, we need to know the percentile, or the area to the left of where we're at. And we're at the 6 ounces, but what is the percentile of being with a 6-ounce cup? Well, if there's 2% above, then there's 98% below. 98% of the time, a 6-ounce cup, it's going to have just enough soda in it. It's not going to overflow. So we would need to type in not 0.02 for the area, but 0.98 for the area. Now, you might go, but we don't know the mean. It's true, we don't know the mean. So what we're going to do is use a normal distribution that we do know the mean and the standard deviation of, and that would be the standard normal. So we're going to say that the mean is 0 and the standard deviation is worth 1. And so now we're going to know what that 6-ounce cup really is in terms of a z-score. How many standard deviations above the mean is a 6-ounce cup? So if I type in my calculator, inverse norm, 0.98, and I leave mu at 0 and standard deviation of 1, then that gives me approximately 2.054. And again, that number is a z-score for this 6-ounce cup. A 6-ounce cup is a little over 2 standard deviations above the mean. All right, so now we can use the z-score formula. Z equals x minus mu over sigma. What's the z-score? 2.054. What is the value of x for that specific cup? 6 ounces. What's the mean? We don't know. That's what we're solving for. What's the standard deviation? The 0.4. So now we're just going to algebraically solve this out here. So if I multiply both sides by the standard deviation, so let's multiply both sides by 0.4, so it cancels out over there. 0.4 times 2.054 gives me 0.8216 equals 6 minus mu. So if I subtract this 6 over, then negative mu equals negative 5.1. Well, let's just round to 2 decimal places here. Negative 5.18. Both sides are negative, so if I multiply or divide both sides by negative 1, then the mean is 5.18. And even just guessing and checking with your multiple choice answers, you would have discovered that it was the first one. All right, so again, this problem and the Starbucks problem, I would say are going to be really good, like in-depth multiple choice problems that are either going to make or break your chapter test grade. So be sure that you're comfortable with doing problems like 8 and 10. And that's all for our multiple